All right, so NoSQL. So NoSQL is a umbrella term. Yes. No, no quiz today. No quiz today. Oh, is that why you're all here? Right. So NoSQL. NoSQL is a broad umbrella term for data storage solutions that alternative storage solutions other than that don't use the relational idea, right? Where you split up content into different buckets, and those records refer to each other to reconstruct the data. And certainly these ideas have been around for quite a while, but SQL has been so dominant for several decades that we haven't even considered these other alternatives. But as new challenges have come up, and as the industry has moved towards certain types of applications, other alternatives have been considered. Especially lately, as data, the data that we're generating is become so staggeringly large. We're certainly looking at other ways that we can manage and store and process and represent large amounts of data. We're certainly generating more data than we can ever, even process, right? Also, a lot of the movement towards web applications, applications that are not on your desktop but are being hosted elsewhere, and the communication between your client and these hosted applications has kind of gone towards a particular representation, such as JSON. That has driven also a lot of the interest on how is it that we should store this. Should we, it'd be nice if we could store the data in a format that is friendly to the way we want to consume it on the client. Also, a lot of the considering that in the framework, whatever framework or stack you're using, there's always lots of transformations between the different stacks. From the client, you need to convert it into a Java representation, and then from a Java representation, you need to convert it into using an ORM, convert it into a flat SQL representation, right? So could we optimize some of that so that we can minimize the number of times that we have to convert between the different layers, right? So that also has driven some of that interest on can we agree on some format that makes everybody happy, that is verbose enough, that it has enough meta information, enough data types, right? That we can all feel fine. And so a lot of the new NoSQL databases have gone towards representing things in formats such as JSON, JavaScript object notation, just because JavaScript is the main language of which these web applications have been written in. Anyway, yeah. So we see that with in the early 2010s, 2011, the growth of data has been exponential. We're storing so much data, and obviously that has risen on other interests on how to do data analytics, how to do data mining, and use lots of artificial intelligence ways of identifying patterns and being able to reduce large amounts of information into knowledge, right? So a summary of large amounts of data. Certainly, we're not going to go through it. We need to automate a lot of this process. So lots and lots of big data. How do you make data that is large, right? That contains lots of data, but also is meaningful geographically to different parts of the world, right? When I'm doing searches or when I'm looking for data, I want it to be meaningful within my own geographical area. Also, I like to be able to make it robust. if a particular data center goes down, that I might be able to survive, some catastrophic failures. And usually, a lot of these data centers create some redundancy in the system that are backed up over large geographical areas. That there's things that typically are not good in small databases where we try to avoid redundancy. These data centers actually look for redundancy and be able to reconstruct data that might be lost from other parts that might live across a large area network. So lots and lots of big challenges to deal with big data and NoSQL. We see that a lot of the responsibilities that we typically give to databases are being moved away from the databases and moved over to perhaps the application level, right? Where instead of giving the database the responsibility of maintaining referential integrity or uniqueness or redundancy or validation of the data, those things are being moved away from the database and perhaps moved over to the responsibility of the application level, right? So no longer is a database going to be responsible for maintaining a schema or validation or anything like that. It should maybe focus on what it does best, right? Very fast storage and retrieval, very fast querying, indexing, survival across a large network, and then move some of that responsibility over to the application level, since we already do a lot of that in the application level, right? Already we already are strongly typed at the application level, right? We already have a data model at the application level. Why reconstruct all that and reapply that at the database level, right? So we'll see today that, for instance, Mongo in particular, they have a relaxed data integrity. Our long gons will be the joins of reconstructing data from multiple buckets into joining fields from multiple tables to reconstruct the original data. The key value is be able to store and retrieve. No use of schemas, and move all that to the application level, right? So make it very, very simple. Just storage and retrieval. Storage and retrieval. It reduces maintenance costs. So there's very little need for a dedicated DBA to maintain the health of the database, right? So it becomes very, very simple. And you give a lot of that responsibility now to the application, or the developers. The developers are going to be responsible for a lot of that. So we're still in the early stages of NoSQL and big data. It's the industry is evolving very, very fast, and so there's the concern of whether these technologies are mature enough for production. For real applications, a lot of it is open source. A lot of it is by community members that are supporting a lot of these efforts, and you still see a lot of large companies being hesitant of using some of these open source solutions. They prefer going with brands. Large brands that might give them much better support in the long run, that they can just call somebody and have somebody come and help them. There's still not enough folks that are experts at using these alternative storage solutions. So it's slowly growing, but steadily. Lots of different vendors that provide NoSQL solutions. This is just a couple of them: Cassandra, Apache HBase, MongoDB, Hadoop. There's a whole bunch of them. There's tons of them out there. We're going to be focusing on MongoDB today, but a lot of these are competing with the same ideas. Again, lots of things that we would take for granted in a relational database, like joining, referential integrity, schemas, validation. All these are, they're disappearing, right? They're not the responsibility of the database. All right, so let's move over to Mongo. Yeah, so we're going to be focusing mostly on MongoDB as the database, the NoSQL solution that we're going to be considering in this course. So MongoDB, you can download it from mongodb.org. They'll try to sell you a paid for solution, but if you search for a community version, community edition, you can download it for free, right? Install it, and that should be enough, right? For this course. So if you download that and install that, you can work on the next assignment. Once you've installed it, you'll need to do a couple of configuration. Like all databases, they expect for you to have a particular file directory where it's going to store its data. Same thing with Mongo. You'll need to create a directory in your file system, typically /data/db. Off of the root directory. That's the default location of where it's going to store the data. And when you install it, there's quite a few executables in the installation. Under the bin directory, you'll find 10 different executables. Two of them are of interest to us. One of them is the server itself, right, that you can run from the command line. It's called MongoD. Right, and that will boot up the server listening at a particular port. The other one is the client that we can use to interact with the database, right? And that was called Mongo. So MongoD and Mongo. Right, so those two are the ones that there's quite a few other that are for administration purposes, for like importing or exporting data, doing some manipulation of that data, some administration parts that we're not going to look into. So if you're on Mac OS, you'll probably need to use sudo to create these directories off of the root. So to start the server, you'll type MongoD. If you're on Windows, you can just type MongoD. If you're on Mac, you might need to put sudo in front of it, and that will start the database. Once it starts, it listens at a particular port in 27017. That's the default port. Although you can configure all these. You can configure the port. You can configure where the data is stored. Those are all configurable parameters. Once it's running, you can start the shell program. The shell is called Mongo. If you type that will bring you it'll connect to the default location of the server, and you can start interacting with it. Right? So let's go over just a couple of instructions. You can list the databases by saying show DBs from the command line interface, and it'll list all the databases that are currently being tracked by Mongo. This is the data model that we've been looking at for the semester. So let's take a look at how would we represent some of this in MongoDB. So we have inheritance. We have user, faculty, and students inherit from user. There is no inheritance in Mongo, just like there is no inheritance in relational databases. So you would have to use similar techniques that we would use in relational databases. You would have to perhaps either flatten the data model, perhaps into a denormalized user that contains all the fields of student and faculty, right? And denormalized onto user, or have a couple of some of the features in some of the properties in user and some of the other properties in student and faculty. But there's no join, right? And in SQL, what you would do is to reconstruct a faculty, you would join user and faculty. Okay, so there is no support for joins, right? Joins. If you want to do a join per se, you would have to do it at the application level, right? You would have to maintain some kind of foreign key saying that this faculty somehow is related to that user. And at the application level, you would need to load the users, load the faculties where a particular primary key matches, right? So the join would be at the application level, not at the database level. Although we'll see in a bit, we'll see that we'll be using an ORM, well, not ORM, a driver that can connect to a database and kind of give us the sense, somewhat looks like a join, but it's not really, right? It'll be something we would have to write ourselves, right? Where we find the user that has this particular ID, find the faculty that has this particular ID, and read from both of them, and join it ourselves manually. We'll see. We're going to be using a driver to do that. We won't be doing that by hand. Okay. So no support for inheritance, but there'll be some support for something that looks like a join in a minute. We also have one-to-manys. We have a couple of many. We have a many-to-many over here, and we'll see that although in relational databases, there's only a few ways that you can represent this. Actually, in a relational database, there's only one way that you can represent this, right? Is that having a foreign key on this side that references the primary key on that side, right? And here in a many-to-many, there's only one way really to represent this. You need a table in between, right? And then foreign keys that go to both. We'll see in a minute that in MongoDB you actually have multiple ways of representing that, right? Certainly the classical way of having the mapping table that references both records. But in Mongo, because in JSON you can have nested properties, right? You could actually represent it with arrays. You can represent the student has an array of sections, and sections can have an array of students, right? Which is basically that's what a many-to-many is, right? If in a relational database you can't do that because you don't have the array data type, right? Where one record can have multiple references to many records, right? So there's no such equivalence in a relational database. But we'll see later in Mongo that we can actually implement this the way it was designed originally, right? So we'll play with that. So you can create a brand new database or schema. Well, no schema. It's a database. By typing use and then the name of the database that you want to use. And it switches over to that. So now every single command goes directed to that particular database. You can now that you're using a particular database, you can start inserting data, retrieving data, manipulating any data. In SQL, you would be manipulating tables and records, yes, but no such thing in MongoDB. Instead of tables, we say that these are collections of documents. So it's not tables containing records. We say that these are collections containing documents. So collections is two tables. And all commands that to interact with a collection, they all start with DB. You say DB dot the name of the collection that you want to manipulate, and then the command, right? The command, whether you want to insert, whether you want to delete, you want to retrieve things, you want to update and manipulate data that's already there. So these are the four basic commands that you can use there. And then you can these are all functions that take arguments And the arguments are interpreted differently depending on the command. If you're inserting, then this might be a JSON object that you are inserting into a database. If you are updating, typically that would be, find me the document that you're manipulating, and here are the new values for that document. So we'll play around with this with a couple of these. We have here's an example of inserting a piece of data, inserting a user Ada Lovelace, username, first name, last name, and the JSON that we are inserting into the database, right? Now, if the user, notice that the user is the name of the collection that we're inserting into. If the collection doesn't exist, it creates the collection by default, right? And then this inserts the record into that collection. So this is what a document. What we insert in Mongo are not, we don't call them records, we call them documents. We call them documents, and they're just plain old JSON represented in JSON format, right? We have name-value pairs with curly brackets separated by commas, and so these are the fields: the field colon value, and so on and so forth. Now, the interesting part here is that the values can themselves be JSON expressions, right? They can be arrays of objects of arrays of arrays of objects. So you can nest them as complex as you want, right? So you can store an entirely fairly complex JSON object into as a record. So a record would be one big JSON object in there. So what you would have normally stored as multiple tables, right, with multiple records spread over multiple tables, right? In JSON, right, in MongoDB, the preferred way of storing it would be as a complex object, right? Where you can have the nesting of objects within objects within objects, as opposed to multiple tables, right? Multiple records spread over multiple tables. Okay, so that is the preferred way of storing in Mongo. Oftentimes we can't do that. It depends on the use case. It depends what is it that, if it makes sense to embed things instead of other objects. So a collection, collection is multiple documents, right? Each one being a separate JSON object. Once you have several collections in there, you can display the list of collections by saying show collections. You can retrieve a particular document by using a find. db.user.find retrieves all the records, all the documents in there. You'll notice that records will have an additional field in there that we didn't generate. It's the _ID field. It's a managed field by the database. It has that particular name. If it has an underscore, it's considered to be a managed field, and a value generated by the database to uniquely identify that particular record. You can retrieve it and list them so that they're easier to read by appending .pretty at the end of the find method. Although you can just, so these are considered transformation functions that transform the data. Don't modify it per se. The values are the same, but they modify them in such a way that might be a little more convenient for us. Right? So pretty just adds white spaces such as tabs and new lines and whatnot for us to parse it a little better. But there's other ones like .sort, right? That sorts it in a particular order. There's .limit, right? That allows you to look at a particular slice of the data set. You can also retrieve a particular record, based if you provide an argument to the find method, that will be used as a filter, as a match to match those records that match that particular subset. Okay? Or you can do it. You can match the ID. or you can match a particular field or combination of fields, a particular username or password. You can combine several fields. They will be kind of like ANDed together, right? The ones that they match will be ANDed together. You can also use projection. If you remember, projection was being able to select which fields do you want. I mean, you might not want all the fields, right? When you're retrieving something from a database, you do that with a second argument. The second argument allows you to list all the fields that you want. By default, you get all the fields, right? By default, you get all the fields. But you can instead provide the list of fields that you want, and 1 means that you want it, 0 you don't want it. Although you always get the ID. The ID you always get, right? Unless you explicitly say that you don't want the primary key. All right, so let's play around with section, and we can create a couple of sections. db.section insert and insert several sections. There we have 4 sections, and we can create several courses. So here we have let's see, we actually no. Here we have retrieving from section. Those sections whose course is CS 101. So notice that we're using we're using that course as if it were a foreign key, right? Referencing some course that has a particular ID, right? So here we're retrieving all the sections for that particular course, and it retrieves all the fields, right? Including the seats, the section, the ID. And it's because we don't have any projection, right? We're just retrieving all the courses. We can narrow it a little bit down. For instance, we can say, give me the courses, CS 101, but I only want the ones that have whose seats is equal exactly to 12. Right? Only retrieve that particular course. And notice that it retrieves only one of them. Right? It doesn't retrieve multiple of these. Or you can also do some Boolean expression where you can compare fields against a particular value. So here, for instance, we're saying we want all the sections whose seats are greater than 30, right? Indeed, we're retrieving all the sections with these particular seats, right? Or you can be a little more complex and use Boolean expression and say that I want all the sections are within, between the seats are greater than 30 or less than 40. Notice the $ in front of it, right? These are special keywords for Mongo that mean something special. So for instance, we have the $ and to be able to and multiple expressions. Here are, we're comparing seats against 30 or seats against 40, less than or greater than. There's also or, there's also not. There's several of these $ expressions, right? As I mentioned earlier, we have pretty, right? Pretty allows us to format the data in a particular easier for us to read. But there's also sort. There's also limit, right? So sort, whatever we retrieve from the data, we can sort it and so that it's in a particular order. And you can sort it by multiple fields. You can say, well, sort first by seats, comma, and then you can provide any number of other fields. So it'll sort by one, and then by the other, and then the other, and so on and so forth. And whether it's +1 or -1, you can sort or in ascending or descending order. Okay. So here's the way it kind of works. You have these filterings that happen where you have the original collection, You have the query criteria that says, only retrieve for me the users who have a particular age greater than 18. So that subset of the records can then be modified by a modifier, .sort. So .pretty, .sort, .limit, those are all modifiers. In this case, the modifier is reorganizing the data to be in a particular order based on age. So here's just a couple more of these comparisons. We looked at greater than, we looked at less than, but there's a whole bunch of them in there, right? And surely we're not going to cover all of them, but there's equal, greater than or equal, in, less than or equal, not equal, not in, and there's tons of them. So I welcome you to take a look at their Mongo's documentation. There's a link there. We looked at $and for Boolean expression, but certainly there's many more. There's not, nor, and there's or. There's also a couple of aggregators, just like you would expect, right? You can group by, you can limit, you can skip, although skip is not very efficient, especially with really, really large data. Unfortunately, the way it works is that it first reads all the records, right? So if you have a long-running query that returns, millions of records, it would have to first limit would iterate over all the elements, millions of elements, before getting to the one that you want to skip over. Okay, so it's very, very slow. So they're working on that. Hopefully, in the next version, they should have a much better implementation of skip. So update works with records that already exist, and allows you to first identify a particular record that you want to modify. So the first argument to the update identifies which record do you want to modify. I keep saying record. Which document in the collection you want to modify. So this is kind of a filter saying I want to modify the record whose name is 02, so I want to find the section whose name is 02, and I want to modify the seats. So notice that we're using set. So set, as you would expect, modifies that particular field and changes its value to the new value. And you get some reply saying that it was successful or not. And then we can see that it has gone from 23 down to 22. Okay. Deleting, use .remove. And again, the first argument here, just like update, just like find, right? Most of these functions take as first argument a filtering object, saying that we're going to pattern match the objects based on that JSON, and the ones that match, that's who I'm going to apply the operation. So .remove, and then we're removing the section with ID whose name is 02. There's quite a bit of other commands for insertion. You can insert one, you can insert many. Mostly we're just going to use the regular insert that allows you to insert a document or multiple documents into a collection. There's several update commands. We just looked at the last one. Delete. All right, so modeling. All right, so generalization. So as I mentioned earlier, inheritance is not supported, right? So there's a couple of options, right? Just like in relational databases, also is not supported. So we look to ways in which we could represent that. Okay. So for instance, if we might have two faculties, in this case we might have Ada and Tim Berners-Lee, T. Lee. Clee, both of them faculty, and we could, for instance, we could here we are adding a couple of fields to Ada. We're saying that Ada notice that we're adding these two fields to Ada, right? The type of user is a faculty, and Ada has an office. So all faculties have an office. So Tim Berners-Lee also has an office. Right, they're right next to each other, I guess. And then I can retrieve all the faculty, right? I can retrieve all the faculty. So we could use the type very much like in JPA. We have the D type, right? When you create an inheritance relationship in JPA, JPA creates this discriminator, right? This discriminating field, so that it can keep track of what was the original class that was used to instantiate that object. Yes. So very similar. We can use something similar to that, and using type to know what type of this is. So we could have a faculty, a student, a staff. We could have all sorts of different types, each one with different values, different fields. So here, for instance, we're creating John, Jane. Both of them are students, and because they're students, now they have a GPA, right? So faculties don't have GPAs, students have a GPA. So here we created John and Jane, both of them as type student. So we inserted them already with a type, right? As opposed to Tim Berners-Lee and Ada. They were not faculty. We made them faculty. We updated them and made them faculty. Here we're updating Jane to have a GPA of 3.9. And we can certainly retrieve the students, right? So yeah, so that's as far as we can get with for implementing a denormalized data model, right? For inheritance, one collection, and the collections can contain both, right? It can contain faculty and can contain students, right? Notice that in non-relational databases like Mongo, it's fine to have two objects, right, in the same collection, but with different schemas, right? I don't know if you noticed that, right? That here we have the faculty. Faculty have offices, but they don't have GPA, right? So some objects have a field office, and some objects don't have a field office, and that's perfectly fine. Right? In relational databases, we would have to explicitly create each one of the fields, right? We would have to create a schema large enough to support both faculty and students. And the problem with that typically is that most of those fields will be null, right? Because for faculty, all the GPA fields will be null, correct? And for all the students, the office field will be null, right? So you have lots and lots of wasted space, right? When you store this for long-term storage, but not so in non-relational databases. In non-relational database, you only store the fields that you have for a particular record document, right? So for instance, for the Jane user, I only have username, type, and GPA. I don't have office whatsoever. So I'm not wasting space remembering that office is null, right? There's no wasted space there. So we don't have those kinds of issues. Again, there's no schema to speak of in Mongo, which could be a blessing, right? So generalization is fairly simple. We basically use the denormalized strategy, right? And call it a day. Let's take a look at many-to-many. So for instance, in enrollment, right, where you have students and sections, typically in a relational database, you only have one way to implement this. Right? The only way to implement this is to have a separate table, right? And that table has foreign keys, right? It has foreign keys to students. It has foreign keys to sections, right? That is basically it. That's it. That's the only way you can represent that in a relational database, right? Not so in non-relational databases, right? You have the choices are much broader. Okay. Certainly, we can go with the legacy way of doing it. You can have a collection, and that collection can have pointing to either one or the other, to the IDs, right? The primary keys of both. So certainly we have the classical way of representing it, just like we do in relational databases, right? But that's not the only representation. There are other alternative representations. Let's take a look at them. So we could have a separate enrollment collection, right? That has references to the other two. Right? So we could have a particular enrollment that have fields such as section and student that have as values the primary keys of both. This is the legacy way of representing it, right? You have foreign keys, right, where the enrollments point to the section and point to the student. Okay, but that's not the only representation. That's not the only way that we could do it. We could instead, what we could do is that a student could have a field called sections that contains an array of sections, right? And where each one of these is a foreign key pointing to the section that they're enrolled in. Right? So this is, and vice versa, right? You could have the section can point to the students that are enrolled in that section. So basically, records pointing to each other, right? Saying, hey, this section, those students are enrolled in this section, and vice versa. On the other side, the students can point to all the sections that they are enrolled in. Okay. Without any need for an intermediate mapping table. See that? Okay. Now, there's a couple of pros and cons, right? Notice that if I were to unenroll somebody, right, notice that here in the enrollment collection, if I want to unenroll a student from a section, the only thing I need to do is just destroy or remove the enrollment 1. And that's it. The student is unenrolled. There's nowhere else represented that this student is enrolled in any particular section. Make sense? Right? So that's easy. But here in this representation, it's a little bit trickier, right? Because if I unenroll a particular student from a section, I need to find that section from this array and remove it, right? But I also need to update the section. I need to go to a section, find the student who just unenrolled, and remove him from this array as well. So it's a little trickier here, right? It's more intuitive. It's more intuitive having this implementation of arrays and whatnot, and not having to have this intermediate representation of an enrollment. But it has its tricks, right? That you need to be careful, right? That you need to update both. It's not automatic, right? You would need to update both. So here's an example of enrolling where we're enrolling into the enrollment collection that a particular section has this particular student enrolled. And this, again, this would be the only record that would show a particular student enrolled in that section. Or if you go the other implementation, you can from the section you can set the list of students. Say that this particular section has this particular student enrolled in it, right? So you have students and then an array of all the students enrolled in that particular section. And if a new student would enroll, you can grab that section and then push into the students the new ID of that new student that is enrolling into that section. Right. So basically, you would end up with that section's students field containing an additional student in there. Okay. Or vice versa, right? We can update the student. I think this is supposed to be student. Right, just like we told the sections all the students that enroll in that section, you would need to do vice versa. You would need to tell the student which sections are they enrolled in. Right? So we can say, oh, students, you are enrolled in these sections, and this other section additionally. I can push, I can update and add more sections that the student is enrolled in. Okay. So one-to-many is fairly simple. Again, here in a relational database, we do have two ways that we can represent that, right? In a relational database, we could represent that. The easiest way, the typical way that we represent one-to-many, is that the children, right, on the weak side have foreign keys pointing to the strong side, right? We just have a foreign key pointing to the primary key. Same thing here. Foreign key pointing to the primary key. Foreign key pointing to the primary key. That's the classical way of representing it. We could also represent it with a mapping table, but that's more uncommon, right? Where the mapping table would map one faculty with many courses, one faculty to many sections, one course to many sections, right? And you would have a mapping table in between. That's more uncommon, right? But the more typical way is to have foreign keys, right? Sections point to courses and so on and so forth. Right? So in Mongo, you have more options, right? You don't just have the foreign key, although you can certainly do that, right? You can certainly go that way. You could say, given a particular section, I can keep track of the faculty ID that is teaching that section. Right, I can point to that. I can have this equal to that particular faculty's ID. Same thing for the course. I can point to who authored this course and point to the faculty ID. But again, that's not the only way to implement it. Instead, you have a couple of other alternatives. Is that how you spell taught? Okay. Yeah. So instead of using the legacy common way that we of foreign keys, instead we could have faculty referencing, right, in an array of all the sections that faculty is teaching, right? Or the faculty can also have an array of all the courses that faculty is teaching. Right, have references, have these IDs of those courses, so we know which ones are being taught. Okay, or there's yet another alternative. Right, the other alternative would be to, instead of storing here the ID of those objects, you can actually embed the entire object, right, as part of the data structure of the parent object. So the parent object can actually contain, as one of its fields, the value of that field is the actual object, right? With all the curly brackets and all the fields and all the values, right, all inside the parent object, right? So this is much more object-oriented, right? This is something that you would expect. If you're storing a Java object, right, and a Java object containing other objects containing other objects, and you have all these references between them, right, and maybe you serialize it to the file system. You can do that, right, with RMI, right? RMI, you can serialize an entire Java object to the file system, and later on you can reconstruct that object. You can read it from the file system and reconstruct the original object into memory, right? So this is something similar. You can have objects within objects within objects, right? And this is being stored, complete inside of the database. So that's pretty powerful. Now, whether you would want to do something like that or not depends, right? It depends on whether you want to be able to access these objects outside of the context of the parent object. Okay, if it makes sense. Does it make sense to access all the sections outside of the context of the faculty who's teaching it? Well, yeah, of course, right? Sections should be able to exist without the need of a faculty. Yes? We could switch the faculty around. It's the same section. So it would make no sense to choose to have these objects live, as part of the data structure of the faculty. Okay? It might make sense to have them as references. That makes sense. That's okay. Right? I'm keeping track of all the sections that I'm teaching. That's okay. But the objects themselves might make no sense. Although there might be things that might make sense. Maybe I have a playlist of songs, right? And maybe my playlist might contain, well, no, actually that makes no sense either. I was going to say that this might contain the actual objects of the songs, right? It might make no sense that I store the songs here. If I remove the playlist, all those songs would be gone too, because that makes no sense, yes? So let's see, what would make sense? So for instance, if you keep track of, so it depends on the granularity of what you're keeping here. So maybe you have a books that might contain different chapters, and if you remove the record of the book, would it make sense to keep track of the chapters, right? If you're storing that, right? Would the chapters of a book make sense to be stored in a separate collection that you have references to? Probably not, right? If you destroy the record of the book, probably all the chapters should go with it, right? So it might make sense that a book might contain multiple chapters, or maybe a book contains modules. Those modules contain different chapters. Those chapters might contain multiple sections. Would it make sense to keep a module in a book? If I don't have the record of the module, it makes no sense, right? So in that case, it might make sense to contain all the objects within here, right? And then if I remove the parent, all the children go away with it as well. Yes? Again, it depends what the use cases are, right? Whether you represent it one way or another. Now, MongoDB prefers to store it this way. This is typically the preferred suggested way that data should be stored, right? Big objects, right? Complex objects containing multiple embedded objects inside of each other, right? To minimize any need to do multiple queries, right? Where you get me the students, get me the faculty, get me the sections, get me, and then you have to join that together at the application level. That's very expensive, right? So ideally, if you can, if the use cases allow it, right, you would store large objects in the database, right? And when you query, you get the entire object into memory, right? And now you can process the entire object, because typically the time what's expensive here is the I/O, right? The input/output access to the file system retrieving this data, right? That's the most expensive part of this. If you can minimize those queries, right? Imagine that I need to go fetch the faculty and the students and the courses, and those are all I/O, right? Lots and lots of queries, small little queries. That's very expensive, time-consuming. If you could bring the entire data over to in RAM, right? RAM is cheap, it's very fast, and you can cache all this in RAM. So that's the preferred way of storing things. So here's an example where you have sections where we are updating the faculty, referencing. So the section here it has a foreign key, presumably, right? That it's referencing the faculty who's teaching this particular section. Right? So this is a classical way, right? Where you have one-to-many. You have multiple sections referencing the faculty who's teaching that section. So embedded instances is the preferred way of storing things. Notice here that we're using the empty triangle. Yes. And typically, we mean by that is that this is an aggregation, yes? Meaning that faculties have references to courses, right? References to sections, and the life cycle, the lifespan of one does not imply anything about the lifespan of the other. Meaning that if I destroy a record in faculty, I don't necessarily destroy the record in course, right? Makes sense. Right? If I remove the record in faculty, I don't necessarily remove the record in course. I don't necessarily remove the record in section. Right? These are just soft references back and forth. Right? But if we had chosen to use instead of aggregations, we might have chosen instead composition, right? Notice that we're using here filled-in diamonds. This filled-in diamond says that this is a composition, meaning the life cycle between these two now matters, right? If I remove one, then the other also has to be removed, right? Which in this example makes no sense, right? That if I remove the course, I also remove the module. Well, actually, no, here it does make sense. I'm sorry, it doesn't make sense between the faculty and the course, right? If I remove the faculty, it makes no sense to remove the course. But if I remove a course, it might make sense to remove a module. If I remove a module, it makes sense to remove the sections or the topics. Right? If I don't have a course, what's the point of having modules? Right? Of having a section or chapter in there, right? It makes no sense. So here, it might make sense to embed modules into the course, embed the sections inside of a module, embed the topics inside of a module section. Make sense? Right? If I remove one, it removes all the other ones. So how would you implement that? So for instance, here we're implementing a topic, and we are, the topic label is embedding object instances. That's the topic of the day. Right? That's what we're talking about. And here, a section might have multiple topics. Topic 1, topic 2, topic 3. Embedded, these are actual objects embedded inside of, so it's an array of objects in there. And then a module might have multiple module sections with a whole bunch of module sections. Module section 1, module section 2, 3, 4. So notice that these are embedded. These are not IDs. Right? These are not IDs. Right? These are the actual object living in there. And finally, at the top, we have a course made up of multiple modules, an array of actual modules. Right? So notice that here, indeed, if I remove the course, all the modules go away. And also the sections and also the topics. Everything goes away. Right? In effect, implementing the composition, right? That one is composed of others. Make sense? And again, it depends whether it makes sense or not. Right? You choose whether it's aggregation or composition. When it's composition, certainly means that you can implement it as embedded objects, one inside of another. Right? And if it's an aggregation, typically it's just a reference. You're referencing that object, not embedded, and the life cycle does not affect it. All right, so how would you, yes? I'm sorry? If we use this embedded object into many, would that be a problem? Well, right, so you wouldn't, right? Because you would have redundancy of that object being copied multiple times, where typically you would prefer to have just references to those objects that already exist, yeah. But you can. Not that you would want to, but you can. So nothing would stop you from doing that. All right, so let's see. So here we have a module, and we are creating a brand new module whose name is Module 1. And has sections that contains an object. So notice that it has an embedded sections. You notice it's an array, and right now it has one section. And that section is called section 1. Right, so notice that that section object right there does not live anywhere outside of the module. Okay, there is no outside section collection, right? Well, there's sections where students can enroll in. That's not the same thing, right? There's a module section. It's not a section where students enroll in, right? So yeah, so that object only lives embedded, right, inside of an array, inside of a field of a larger object. See that? Right. So that's what we refer to as an embedded object. It's inside. What Mongo will do is that it will also keep track of this as a unique identifier, but it's not shown here. And we can push another section. We can say, hey module, here's another section. Let's push section 2 into sections. And here it is. We can say module, and these are the 2 sections that notice that only ever exist as embedded inside of the parent module. Yes? Okay. So let's keep going. Let's see. Right. So just like we can retrieve an object, you can also navigate inside of the embedded objects. Find me things that are embedded in there. Right. Notice that the way you would do this in a relational database, you can't. Well, first of all, you can't do this in a relational database. Right. You would have to have a table called modules. You would have to have a separate table called sections, and those sections would have to have foreign keys back to the module, right? Saying that these modules belong to that. That these sections belong to that module. Yes. Okay. And if you want to retrieve sections of a particular module, you would have to join them. You would have to say, hey, these are the sections for that particular module, and you know the foreign key, primary key reference. Yes? Here, there's no such thing. You can just say module.sections, and you immediately have the sections array. Right? There's no need for joining these. But the interesting part might be that I might want to retrieve the sections inside of a module. And Mongo provides a syntax to do that. We can say from the module, right? Find me the module whose module name is module 1, right? And I only want the sections. That's all I want. I don't want the name. I don't want to know how many people have read this module or whatever, or the last time it was updated. I only want the sections. And indeed, that's all we get, right? Plus, obviously, the ubiquitous underscore ID. We always get that. There they are, sections, and the sections we wanted, the array of the sections, which is fine, right? That's what we would expect. But soon we'll hit a limitation in the current version of Mongo, and we'll see what that is. How about now we start adding more things in here, right? Let's see. One of the things that we would like to do is that we have a module. We have two sections in that module, and let's see. Let's keep track of this. So we have here one big module, module 1. Module 1, right? And module 1 has sections. Sections has 2 sections, right? Another section here, right? So this is the first section. Now we would like to be able to put in here maybe a topic, the topics in a particular section, right? And there might be multiple topics here. Right? And maybe each topic might have widgets and might have a whole bunch of stuff in there, embedded in there. So let's see where this gets somewhat hairy, right? That's somewhat challenging. Here we're grabbing the module. Which module? Well, the module whose name is module 1. Okay? But I want to update the first section. I want to maybe grab this section or that section, right? And grabbing that section, I like to be able to maybe add a topic to that section. See that? Now it's getting complicated, right? We're saying name of the module is module 1, but then I want a particular section. So we can say sections.name section 1. See that? Now I'm basically saying module 1, and then the section whose name is section 1. So this is section 1 over here. So it says this is section 1, and this is section 2. All right, so the one that's section 1. And so now we've identified exactly which section we want to modify, right? Once we modify it, once we identify the record, we want to update it. We want to say, hey, that particular section that we're in, right? I want to add something to it, right? I want to add a field called topics, right? A field called topics, right? Because I want to push something in there. I want to put something in there. I want to put a topic whose name is topic 1 that is one of multiple topics in an array. So topics is an array whose first topic is topic number 1. And notice this weird $sign there, right? This $sign is an index operator that says, whichever section that you're in. I don't know which one. Is it the first one? Is it the second one? I don't know which one. Now, you tell me. It's the one that matched this one. Which index was it? Was it the first one, 0? Was it 1, 2, 3? Which one was it? I don't know. Well, this one is, the current index, right? So if it was 0, then that $sign is 0. If it was number 1, number 2, number 23, then that $sign is 23. Make sense? All right. All right. Once we've done that, notice that indeed we were able to add the topics, right? That first topic as an array, right? Notice that we have section 1, section 2. Neither had a topics, but now we were able to add topics to the first section. Right? So notice that sections.name allows us to navigate through this JSON object, right? We have the module whose name is module 1, dot sections, right? Dot sections, dot topics. So this $sign is saying it's this section, not this one, is section sub 0, right? And then inside we're creating topics that contains this one topic, right? Make sense? All right. All right. So that worked, so let's make this a little more complicated. We had module. The module contains sections. The section contains topics, right? We have that nesting. We have this nesting. Let's put this whole module inside of a course, right? Because this is one module of many modules that make up an entire course, right? So remember the data model, right? We have one course containing many modules, one module containing many sections, and one section containing many topics. Yes? So we have one module. We just created one module, module 1. Let's add that module into a course. So here we're creating a course. We're creating that course there with name course 1. And we're updating that course and adding an empty array of modules. So there it is. There's our modules. Okay, and here we are pushing. We're pushing a module. Actually, we're kind of going over it again, right? We're slowly going to build a course, and we're going to add a module. Then we add a section. Then we add a topic. I just want to show you where the limits of this. Here we're pushing a module, module 1, right? Then we're going to push another module. There it is. We have a second module. So one module, second module. We're going to add a section. We're going to say, grab me the module whose name is module 1. There it is. So this is the course 1. And I'm looking under modules, name module 1. Add a section. There it is. We're pushing a section, section 1. And now we would like to push a topic. We're going to navigate down to course, down to modules, down to section, and now we want to push a topic in there. But to do that, just like we needed the $sign to navigate to the section, to navigate down to the topics, we're going to need another $sign. And that's not allowed. That's not allowed in Mongo. In Mongo, we can't have two index operators. Right? And this is where the limit of the current Mongo implementation leaves it now. For instance, we could, if we knew that it was the 0th index, if we knew it was 0, we could use the literal 0 or 1 or 2 or 3. But the $, that's not allowed. So it's a limitation of the current Mongo database implementation. They're working to resolve this, since it might be something very common that we might want to do, right? And that's where Mongoose.js comes in. Right? Mongoose.js. We need to be able to do some of these operations. Instead of doing it at the database level, we're going to need to do this at the application level, right? We need to be able to do this programmatically as opposed to from the database, right? And that's what we're going to be looking at next.